Nice. Finally. Cool.
I'm really sorry about it.
No worries at all. No worries at all. So then, welcome back, everyone. Let's make a quick start. So our next speaker is Cecile Della Valle. And so she's a PhD student at Paris Université, Map 5, and supervised by Sylvain Durin. And she will talk about inversion of integral models. Stage is yours.
Okay. Okay. So hi everyone. So I will present a work that I have done with Émilie Chouznou and Jean-Christophe Pesquet on inversion of integrals models using a neural network. And more specifically, I'm going to focus on Abel integral. So first, I will present the biophysical model that leads to inverting an Abel integral. I will present one model. There are several inverse problems where such operators arises, but here I present only one. Then I present a motivation for our inversion strategy. Then I describe more precisely the method, combining variational approaches and neural network approaches. Then I present the architecture of the neural network. I will discuss stability theoretical result and illustrate this result with numerical experiment. So first, in aggregation phenomenon, you have a cluster of size I containing C particles. And for example, if you have a filament of particle at its end, you can add or retrieve a particle. And you have two types of chemical reaction. So if we put that in a mathematical setting, we have the Lifshitz-Liouvsov equation. So if U is a concentration of a cluster of size X or I at time t, then its concentration satisfies this equation, which is a transport equation of the speed at any time tau. Here you have the initial condition that I denoted minus X, and the last line accounts for the mass conservation in the system. So I just rewrite this equation with the V, the speed of the reaction. And I suppose that I have access to V by another mean. And so now the type of measurement that I can have in such experiment is a moment of order A of the solution U. So a moment can be defined as follows. So it's an integral over the minimum size of the system and the maximum size of the cluster of x power a, the size power a, times u. And now u is linked to its initial function with the characteristic method, since we have a transport equation. Now, by a change of variable, I can rewrite it as an operator acting on x, the initial signal. So my inverse problem is reconstructing u, or equivalently x, from a measurement tx. So t is now an operator from L2 to L2. This operator is in fact a type of Abel integral. So I redefine the Abel integral t minus a x, which is an integral on 0 to t minus s power I minus 1. And I had a kernel here that allows us to account for a larger variety of biophysical model times x. This operator is well defined from L2 to L2 as long as k is an operator from L2 to L2 and x is also, of course. So k is L2 from omega to omega. So now the measurement that I have is y, which is the image of x. Yeah, hello?
No. Camina, down.
Okay.
Camina. Coffee, Camina. Coffee, beer, Camina.
Yeah, sorry. And we don't have access to Y, but
You invent, yeah.
Yeah. So sorry. So we don't have access to Y. We have access to Y delta actually, which is a noisy measurement. So the level of the noise is denoted by delta. So here we want to, our reverse problem is to invert TA. So we're constructing X from a noisy measurement Y delta. So this is why is it ill-posed? So if A is equal to 1, we only have the integral operator. And so the inverse of T1 is just a derivation. But since we have access to Y delta, which is in L2, we have to make sense of the derivation of Y delta, which is not possible. So more generally, all the TA operators are compact and their inverse is not continuous. So one strategy to gain this continuity is to add a regularization term, so to use, a variational method, which is a minimization on a feasible set denoted by C of a data fitting term and a regularization term. So this approach incorporates prior knowledge about solution and enforced desirable constraint and is grounded on clear mathematical concepts, but it has drawbacks. We don't have closed form solutions, so we have to use iterative algorithm. The objective function not always reflect the perceived quality, and estimation of the regularization parameter and the algorithm parameter is time consuming. It is only done by the experiment during experiment, and sometimes we don't have general rules to set these parameters. So on the other hand, in deep learning methods, we have generic method for linear approximation. It's an efficient way for incorporating prior knowledge from big database, which can account for this perceived quality. And the drawbacks, it makes it difficult to account for physical models, and it's the black box. So to combine the benefits of both approaches, we suggest here to unfold optimization algorithm. By unfolding optimization algorithm, what I mean is that instead of iterating an algorithm till convergence or till how we define the convergence, I only unfold the optimization algorithm over a defined number of iterates, and I can plug a neural network in these iterations. So first I define the progressive gradient descent. So if we take only the basic optimization problem, X belongs to a feasible set, we want to minimize this data fitting term. So one way to do that is the projecting gradient algorithm. So at each iteration, I project on C a gradient descent step of this twice differentiable function. Okay. So now if I rewrite the projected gradient algorithm, I can rewrite it as a linear part applied to Xn and a bias. The linear part depends on the gradient step, the operator, and the bias depends on the measured solution. So now we have almost a feed-forward network. It looks like it because here, instead of a projection, in a feed-forward network, we have an activation function. So I define G, my neural network, which is a combination of linear operator, the sum with the bias, and an activation function. So G is a layer of my neural network. And Wn can be, for example, convolutive operators. So now I still have to make a link between my projection and my activation function. So I define the proximity operator with the set of proper lower semi-convex function. The proximity operator, prox_g, is the argmin of over Hilbert space of G plus 1 to 2 the norm of Z minus X. The special case for an indicator function of the set, then the proximity operator is exactly the projection. So we have a link from the projected gradient algorithm to the forward-backward algorithm. And what I assert here is that most of the activation operators are in fact proximity operators. I will give 2 examples. For example, ReLU is the projection on set 0 plus infinity, but also parametric rectified linear unique ReLU. The prox is it is actually the proximal operator of this function phi. Softmax is also a proximity operator, and this type of computation can be done with a very large variety of activation functions. So our method, let's go back to our problem. I made an assumption to assert that there is a solution to our problem. So I defined the problem P0 to minimize, it's still the same problem, on a feasible set, a data fitting term, and a regularization term. I assume that both terms are twice differentiable, and the sum is either coercive or C is bounded. I define the feasible set as a finite number of conditions. And I said that the interior of the feasible set is not empty. So that provides the existence of a solution to P0. And the twice differentiability is important because in training, we're using stochastic gradient descent. And that is a good property. Okay. So now my constraint problem. So if I imagine that I have a feasible set in between those 2 lines, and this is my function, what I say is that with the projected gradient descent, the projection is not twice differentiable, and we have vanishing gradient issues during training. So that is why we prefer to solve an unconstrained subproblem. I define the logarithmic barrier of my constraint, and instead of minimizing over a subset, I minimize on the whole space, and I had this term, that is this function, and you see that it transforms my my function to minimize and constrain it to be plus infinity outside of my feasible set. So now P0, my problem, is replaced by a subsequence of subproblem P mu, and with the sequence mu tending to 0, I find back the solution of P0. And now the main advantage is that I have feasible iterates. So to solve such a problem, I have the interior point method. I can define my iterates as the proximity operator of my function, but I don't have closed form expression for this proximity operator. So what I do is I come back the forward-backward proximal interior point method. So I do a gradient descent on the differentiable part, and I only compute the proximity operator of the barrier. So now I have to rewrite my algorithm, but I still didn't plug any neural network. So the question that I have now that I have my algorithm is how do I set the parameter, the barrier parameter, and the gradient descent parameter? And I still don't have find the regularization parameter leading to the best quality of the solution. So now I unfold my proximal algorithm over m iteration, and I untie the parameter across the network. So if I define one layer or one block as this operator, I have two inputs, x0 and b0. B0 is linked to the measurement. My neural network is the combination of m block, and in each block I have my operator A, that is my activation function, my proximity operator, the linear part, the bias that is always the same, and all the parameters are computed with neural network. So in my hidden structure, I have one neural network that estimates the step size, one neural network that estimates the barrier parameter, one neural network that estimates regularization parameter, and each are repeated in each block. So, and then in my block structure, I compute this operation that looks like a feed-forward network. So I will describe all the neural network. So to estimate the step size, since the step only depends on the structure of the network, it doesn't depend on the initial solution or initial input or output. I only learn and enforce positivity with the soft plus. So I only learn a scalar. For the barrier parameter, I have two types of constraints that I want to apply. So first, an affine constraint. For my cluster problem, for example, it would mean that the size of a cluster is bounded with two size limit, or hyperslab, which is a bit more tricky. But for example, the mass of the system is the moment of order 1 of my solution, and what I can say is that initially I want to ensure that the mass of the cluster doesn't exceed the total mass of the system. So that would be hyperslab condition. And so the barrier parameter is computed starting from the input of on a block. I do two average pooling and soft plus, and then a fully connected layer plus soft plus. There is, this is experience-based and it works well. And finally, for the regularization parameter, since we choose a regularization that is of the general Tikhonov-type, we have literature that gives up to a constant a theoretical optimal regularization parameter. So I use this formula, and I learn the scalar D in front of the formula. So now, what about the stability of this network? Well, just to recall, there are a lot of issues around stability of network. In deep learning, you know that generally we have a lack of robustness in most classical neural network. And there are a lot of applications with high risk so there is a need for theoretical guarantees and not only experimental guarantees. So a work has been done before on the stability of this type of neural network, and the stability has been computed to perturbation of the input x0. What I had is that I compute a stability to a perturbation of the observed data y delta, which is linked to the bias. So it's almost like computing here the stability of a feed-forward network, and here our residual neural network. So first, I recall what is an average operator, which is a good tool to compute the stability of asymptotic neural networks. So if G is my neural network from an Abel space to an Abel space, G is alpha average if there exists a non-expansive operator R, such that G equal 1 minus alpha identity plus alpha R. So if G is average, it is non-expansive. And if it's average, it respects this type of inequality. And in particular, the output of G is bounded by the input. So I show you here a theoretical result from Combet and Pesquet that we're going to use, we used in our work. If we define W as the combination position of all the linear parts, and we define theta minus m minus 1 as the sum of the norm of combination of W, then I can say that the neural network G, I can exhibit a Lipschitz constant. And I can also say that if this inequality is met, then G is alpha average. So just to show you, what does it do? If M is 2, that means that I have only 2 layers. Then theta 1 is this formula, and theta 1 2 is the Lipschitz constant of G, and the inequality gives us this. So up for a 3-block neural network or 3-layer neural network, the computation is a bit more difficult, but I still can exhibit a Lipschitz constant and a condition for alpha averageness. So the take-home message is that the stability of a neural network depends on its weight operator and not on its activation function. And I have a rule for computing a Lipschitz constant. Even if it's a bit complicated, I still have a rule. So this theorem has been done in a feed-forward architecture. But I don't have exactly a feed-forward architecture. Here, I want to compute the stability on the bias operator, not only on the input. And so to do that, we define a virtual network, which takes as the input Z, which is X and B. And now the activation function is in a larger space of L2 times L2 with one input has the activation function and the other one is the identity. And so now I have to define the norm of a virtual network, and I take a norm on L2. Okay, so now I have the rule to compute my theta, and I have the norm to compute it. So I do all the computation. I still have one assumption that I need to do this computation. I assume that T star T and D, which is a regularization, it's a derivative, are diagonalizable in the same basis. And so I can compute eigenvalues in the same eigenspace. And so I just show you the computation, but I will not detail it. It's just that we can define and compute exactly those two terms. And then thanks to those two terms, I can define the norm of U, which would be like this. And I have studied 2 subcases. If the input is 0 and if the input is equal to B0. So if the input is the measured data. And so now I have a rule also to compute the Lipschitz constant of my neural network, which is linked to the eigenvalues of my two operators. Okay, so now I show you, now that I have a rule to compute my Lipschitz constant, I'm going to apply it to a real neural network. So first, there does not exist a large data set as it does for image for 1D signal of cluster. So we have to build a data set that is coherent with the observation. So obtain a large variety of bimodal or quasi-bimodal signals with variable peak width. So I exhibit, for example, 3 signals that I have, construct. And here I show what types of signal we can measure. So here is a perfect image, and here is a noisy signal for a equal 1. So this is only the integral, and then for a equal 0.5. So for the training, I have 330 signals distributed as follow: 200 for the training set, 100 for the validation set, and 30 for the testing set. I have 4 test configuration: a equal 1 and a equal 0.5, and I have also my affine and hyperslab constraint. I train the neural network end-to-end fashion. My love is MSE. I use PyTorch. And this is the kind of, after training, the kind of output result that I have. So I made 3 remarks. The output errors are low when I compute them. The output signals are smoother than the expected signal. And when I equal 0.5, it gives a better output, which is coherent with this consistent, with the theory, because the problem is less ill-posed when a equal 0.5. And I also have, I can compute now a Lipschitz constant in the 4 subcases that I studied. So what I can say is that the Lipschitz constant do not vary much, neither according to the choice of a nor of the constraint. And also the constants are lower than 1, even very low. And the algorithm tends to constrict the solutions. This can be explained because the space of solution is smaller than the space of the input. So to conclude, neural network architecture built in an is built in an explainable manner. Sorry. We show an efficient method developed by mixing ideas from iterative optimization or variable algorithm and neural network techniques. We also have an expression of the proximity operator of the barrier function and their gradient. I didn't show that, but that's what has been done in this work. There are requirements of better non-convex optimization methods. Optimization concepts are not only useful to train neural networks, but also to analyze them, as I shown with Lipschitz constant and alpha average methods. This is related to Jason. Thank you for your attention.
Thank you very much, Cecile, for a very nice talk. We have a lot of time for questions. Are there any questions either from the physical or the virtual audience? Yes, Claire?
So in the stability part, you have this requirement that two operators need to be jointly diagonalizable. How practical is it? I mean, how do you deal with this assumption in practice? Does it constrain a lot your applications or not?
For the case of the Abel transform, there has work that construct the basis for D and for T. So for the two, and I mean, it's a case-by-case problem. Depending on your operator and the regularization operator that you choose, it might be difficult to have the diagonalization in the same basis. It means that the two operator commutes.
Yeah.
It was a case in our application, but it can be also a limit to this method. Don't know if that answers your question.
It does.
Any further questions?
So it was a really nice talk. Could you please remind me, how did you estimate the step size? So you said that you had a separate network to estimate step size.
The step size, yes, it's just a scalar that is learned. There is no input.
Okay, because you were saying earlier that the step size only depends on the network architecture, rather than any sort of input. I was just curious, how was it learned, considering it depends on the network architecture? I didn't quite get the connection.
Okay. In our neural network, we have a parameter that is used through the network, and we backpropagate on this. But the scalar is learned. I mean, I think so. Okay. Okay, so here the output will depend on the scalar, and I say I just learned the scalar. So it depends on the input because when I compute A, I backpropagate here, but there is no other hidden structure for the gradient step.
Yes, so you learn it through backpropagation.
Yeah, just here. That's it.
Any other questions? Okay.
Yeah. Like more generally, like in your last slide about the outlook, you say that you need more progress on algorithm for convex, not necessarily strictly convex algorithm. Can you explain more precisely what you would need in order to? I mean, what are you looking for?
What am I looking for convex? Well, I was actually I was thinking of the Chambolpock method. But Sorry.
We can also discuss it offline.
Yeah, sorry.
Thank you.
It looks like I think there are no more questions from the audience virtually. Is there anything? No, right? Then let's thank Cecile again.
Thank you.